So this video is covering section 7.7 on intermolecular attractive forces, which are influencing boiling point and melting point. So intermolecular forces are the attractive forces that exist between molecules. So it's forces that attract molecules between themselves. And in order of increasing strength, these are London Dispersion Forces, Dipole-Dipole Interactions, and hydrogen bonding. There is also the Ion-Dipole Interactions, but these exist between ions and molecules. It's not necessarily within the same substance. So the strengths of the intermolecular forces determine whether a compound has a high or low melting point and boiling point. And thus it determines whether it is a solid, liquid, or a gas at a given temperature. So let's go through the intermolecular attractive forces, and let's start with London Dispersion Forces. London dispersion forces are very weak interactions due to the momentary changes in electron density in a molecule. So here you have a molecule of methane, CH4, two molecules of methane, CH4. And you see how there is that white cloud around the molecule. And so this symbolizes the electron cloud. And you can see that because electrons are constantly moving in that cloud, roaming around, there may be times when there is more electron density in one region. And so that would be on the left side of the molecules here. More electron density in one region creates a partial negative charge in that region. And this is symbolized by the delta minus. And then if you have more electron density in that region, that means an opposite area of the electron cloud will be lacking electron. So on the opposite side, you will have less electron density in that region, and that will create a partial positive charge in that region. And this is symbolized by the delta pluses, which are partial positive charges. And that can happen also to a neighbor molecule of methane. And so these partial positive charges and partial negative charges are attracted to each other because they are opposite charges. And so that will create an attraction between these two molecules, for example. So the London dispersion forces are due to those momentary changes in electron density in a molecule. So there is another illustration here to show that with two different atoms, and the electron density is shown with those blue dots. So each blue dot represents an electron, and where you see more dots, where it's more dense, that means there is more electrons there than where it's more clear. And so in the first in the top illustration here, you can see that electrons are more to the right side of the atoms for both atoms. So this creates a partial negative charge on the right side and a partial positive charge on the left side. And so these two atoms will then be attracted to each other due to those opposite charges. But at another instant, all the electrons may be randomly distributed and so well that there is no imbalance in between the distribution of the electrons. And so that would be the second illustration here. And if you go down, at the next instant, the electron density may have changed again, and then you can have more electrons towards the upper left corner of the first atom, and on the second atom it can be in the lower left corner, and still there can be an attraction here because you see that the partial positive charge is almost opposite to the partial negative charge. So that will create a temporary attraction again. And yet again, these electrons are keep moving and are, populating a different area again in the fourth illustration, right? And so on. So the changes in electron density creates temporary dipoles, and the weak interaction between these temporary dipoles constitutes London dispersion forces. So it's forces that are constantly changing, but overall it creates this what we call London dispersion forces of attractions between the atoms. So all covalent compounds exhibit the London dispersion forces because all covalent compounds are made of atoms which have an electron cloud. So all molecules will always exhibit London dispersion forces. So when you are asked to list the intermolecular forces that are happening within a substance, you will always list London dispersion forces. And the larger the molecule, the larger the attractive force, and the stronger the London dispersion forces. That is because the larger the molecule, the more, the larger the electron cloud, right? A larger molecule, we have, more electrons and a larger electron cloud. And so when there is an imbalance, it can create a slightly larger partial positive charge and partial negative charge in the electron cloud that will then attract, another molecule with a opposite charge next to it. So then the stronger the London dispersion forces when you have larger molecules. So you want to remember that if you compare two molecules that exhibit only London dispersion forces. So the second type of intermolecular forces are the dipole-dipole interactions. So dipole interactions are attractive forces between the permanent dipoles of two polar molecules. So here, it's not temporary, momentary dipoles like we had in the London dispersion forces. These are dipoles that are permanent because the molecule is polar. So the illustration here shows a formaldehyde. It's a Lewis structure and then models of it. So you have three formaldehyde molecules. And we know now that the CO molecule is a polar bond. CO bond is a polar bond because oxygen is more electronegative than carbon. So you will have a partial negative charge on oxygen and a partial positive charge on carbon. And so a molecule of formaldehyde will be attracted to another molecule of formaldehyde such that the oxygen will be attracted to the carbon of the other molecule, right? And yet this second molecule, the oxygen of that second molecule will be attracted to the carbon of a third molecule, right? Because it's opposite charges that are attracted to each other. So because of that, then the molecules will arrange themselves such that the oxygens are oriented towards the carbon and the carbon oriented towards the oxygen. And so it gives some kind of order to the substances when you have that kind of dipole-dipole interactions. So the third intermolecular forces is the hydrogen bonding. And so don't be fooled by the fact that it says bonding. It's an attraction, it's not an actual bond. So hydrogen bonding occurs when a hydrogen atom is bonded to an oxygen, a nitrogen, or a fluorine, and is electrostatically attracted to an oxygen, a nitrogen, or a fluorine atom in another molecule, right? Remember how intermolecular forces are forces that act between molecules. Yeah, inter means between, molecular refers to molecules. So it's forces that act between molecules. And it's not bonding, even though here it says hydrogen bonding. And so a molecule that experiences hydrogen bonding is the molecule of water. You see its Lewis structure and then models. You have two models of the molecule of water. And the oxygen of the molecule of water is partially negatively charged, and the hydrogens are partially positively charged. That's because oxygen is more strongly electronegative than hydrogen. So it will attract the electrons towards itself more than hydrogen. And so the oxygens are partially negatively charged and will be attracted by the hydrogens of another molecule. You see that on the left, on the right side, where you have two molecules with the delta pluses and delta minuses showing up. And then the dashed line between the oxygen of the first molecule and the hydrogen of the second molecule are illustrating the attraction between the partially negatively charged oxygen and the partially positively charged hydrogen. And so it's illustrated this way to show that it's not a bond, it's an attraction. So those dashed lines represent attractions, not bonds. And so because of that, water will, orient itself and will be more stable. So hydrogen bonds are the strongest of the three previous types of intermolecular forces. And hydrogen bonding is very important for biological molecules, especially big, large molecules like DNA. The double helix structure of the DNA is due in part to hydrogen bonding between the cytosine, guanine, adenine, and thymine amino acids of the two strands of the DNA. You can see in the zoom of the DNA molecule here how the dashed red lines are illustrating hydrogen bonding between the oxygen of one molecule and the hydrogen that is bonded to a nitrogen of another molecule, or between the hydrogen that is bonded to a nitrogen and the nitrogen of another molecule, right? So the hydrogen has to be bonded to nitrogen, oxygen, or fluorine. Otherwise, the hydrogen cannot form that hydrogen bonding. And it will be attracted to another oxygen, nitrogen, or fluorine of another molecule. So hydrogen bonding is an important intermolecular force. The fourth intermolecular force we will encounter is the ion-dipole interactions. But when we are asked to list intermolecular forces between molecules of the same kind, this will not play out because you need ions and then a molecule that is polar for this to occur, right? It's between two different kinds of molecules. So it's an intermolecular force, but it's a special case, if you will, because you need ions and then polar molecules for this to occur. And the ions, like for example, positive ions in water, the molecules with the red and white spheres are the water molecules. And for example, the negative ends of the water dipoles are surrounding the cations. So that's what happens when you have salts, ionic salts dissolved in water. The water will be able to dissolve the salts because it will take each ion separately and surround it. And the way the cations are surrounded is different than the way the anions are surrounded by molecules of water. cations are surrounded by the oxygen side of the molecules of water. So water is orienting its oxygens towards the cations. And then the anions are surrounded by molecules of water that are showing up their hydrogens first. So it's the hydrogen side of the molecules of water that are turned towards the anion, right? Because it's opposite charges that are attracted. So these ion-dipole interactions are very important. It's what determines the solubility of salts in water, for example. So this table summarizes the type of intermolecular forces that exist. So there is the London Dispersion Forces, that's the weakest. It's exhibited by all molecules. So for example, we saw CH4, formaldehyde and water would also experience that. The dipole-dipole molecular forces are have a moderate strength, and they are only exhibited by molecules with a dipole. You need a net dipole, which means you need a polar molecule for this to occur. Otherwise, it's not possible. Non-polar molecules will not exhibit dipole-dipole interactions. So in our examples, only formaldehyde and water can experience dipole-dipole interactions. Hydrogen bonding is the strongest of those three, and only molecules that have an hydrogen bonded to an oxygen or bonded to a nitrogen or bonded to F that will be able to do hydrogen bonding. And so out of our first three examples, methane cannot experience hydrogen bonding, and formaldehyde neither, because the hydrogens are bonded to carbon, not to an oxygen, a nitrogen, or fluorine. So only water in those examples can make hydrogen bondings between molecules of water. And then the fourth type here, ion-dipole interactions are only happening if you have a mixture of ions and polar molecules. It is a very strong force of attraction. And so this is typical of what happens when you have ionic salt dissolved in water. So let's go through a learning check. For each of the following, list the intermolecular forces. And so it's asking you to list the forces that each molecule experiences with molecules of the same kind. So Cl2 between Cl2, HCN between HCN molecules, and HF between HF molecules, etc. Right? It's not between other molecules of a different kind. It's molecules of the same kind. So within the same pure substance, what are the intermolecular forces that are holding the molecules together? And so that means the ion dipole is not an option when you are asked that kind of question. So Cl2, if we draw the Lewis structure, I will show it here on the right. That's the Lewis structure for Cl2. It's a diatomic molecule made of 2 chlorines. And so if you look at the electronegativities, of course, there will be no electronegativity difference between 2 chlorines because they pull with the same strength. So it's a non-polar molecule. So you want to list the intermolecular forces, and one that you should automatically list for all molecules is the London Dispersion Forces. And in the case of Cl2, because it is non-polar, it cannot experience dipole-dipole interactions because Cl2 has no dipoles, right? Dipoles are for polar molecules. And it doesn't have any hydrogen, so hydrogen bonding is out of the question too. So Cl2 only experiences London Dispersion Forces. Let's look at HCN. The Lewis structure of HCN is given to the right here. You see that the hydrogen is bonded to the C, and the C is triple bonded to the N. And if you look at the electronegativity differences between C and H, this is considered nonpolar, and between C and N, there is a difference of 0.5 between them. And so it's considered a polar bond. And nitrogen has an electronegativity of 3.0, carbon is 2.5. So the arrow that shows the polarity for that bond and the molecule will be pointing towards nitrogen. The carbon is slightly more electropositive. So now if we focus on listing intermolecular forces, HCN experiences London dispersion forces like all molecules. Now you have to decide, does it experience dipole-dipole interactions? And here we have a dipole. This is a polar molecule with a net dipole. So yes, it can experience dipole-dipole interactions. So you would list that too. And the last question is there a possibility for hydrogen bonding between HCN molecules? And the answer is no, because the hydrogen is bonded to carbon. It is not bonded to oxygen, nitrogen, or fluorine, right? So London dispersion forces and dipole-dipole interactions are the only intermolecular attractive forces that HCN can experience. HF. The Lewis structure is given to the right. Fluorine has an electronegativity of 4.0 versus hydrogen 2.1. That's a large difference, and it's a polar bond with the arrow pointing towards fluorine, because fluorine is the most electronegative element of all. So it makes hydrogen slightly electropositive. So if we list the intermolecular forces, we will have the London dispersion forces, like for whole molecule. We need to ask ourselves, do we have dipole-dipole interactions between HF molecules? And yes, we do, because this is a polar molecule with a net dipole. So yes, we have the dipole-dipole interactions. And the last question, do we have hydrogen bonding between HF molecules? And yes, we do, because we have hydrogen bonded to fluorine, and that's a condition for hydrogen bonding to occur. So the HF molecules will be experiencing hydrogen bonding between themselves. The hydrogen will be attracted to the fluorine of another molecule, and the fluorines will be attracted to hydrogens of other molecules. So that's the list for HF. CH3Cl. The Lewis structure is given to the right. The chlorine has, 3 lone pairs, but they are not drawn here. The CH bond is non-polar, but the CCl bond is polar. If you look at the electronegativity difference, carbon has a value of 2.5, chlorine 3.0, so it's a difference of 0.5. So it's a polar molecule with a dipole that is the same as the dipole for the bond. The CCl bond is polar towards the chlorine, because chlorine has the highest electronegativity value. So we have a polar bond here. So if we list the intermolecular forces, we will list London dispersion forces, because all molecules experience that. Dipole-dipole interactions also is exhibited here, because we have a net dipole for this molecule. It's polar. Now, do we experience hydrogen bonding between CH3Cl molecules? No, there is no nitrogen, oxygen, or fluorine. So there cannot be any hydrogen bonding between the CH3Cl molecules. So now let's answer the questions. Which molecule has the strongest intermolecular forces? Out of these 4 molecules, the one that experiences the strongest is the one that has the most intermolecular forces, happening. And here it's HF, right? HF has the three types of intermolecular forces happening for it. So HF will be the one that experiences the strongest intermolecular forces. And then which molecule has the weakest intermolecular forces? So you want to find the molecule that has fewer forces listed. And here it will be Cl2. Cl2 has only London dispersion forces, so it experiences the weakest intermolecular forces between its molecules. So let's do another learning check. And here I will provide the Lewis structures as we go. So list the intermolecular forces for each molecule and rank them in order of intermolecular strength. So water, the Lewis structure of water is given on the right. Water is a polar molecule. The electronegativity difference between oxygen and nitrogen, oxygen and hydrogen, it's 3.5 minus 2.1. It's a difference of 1.4. So the OH bond is polar. It's polar towards the oxygen. So you have 2 little arrows going up towards the oxygen. And so they add up into a net dipole that is going up towards the oxygen. And so the hydrogens are partially positively charged and the oxygen is partially negatively charged. So now let's list the intermolecular forces. So there is always London dispersion forces. Here we have a net dipole, so we will have dipole-dipole interactions. And now, do we have hydrogen bonding? And yes, we have hydrogen bonding because we have HO bonds that creates, partial negative charges on oxygen and partial positive charges on hydrogen. And the hydrogens of one molecule of water will be attracted to the oxygens of another molecule of water. And the oxygens of a molecule of water will be attracted to the hydrogens of yet another molecule of water. And so hydrogen bonding is occurring between molecules of water. C3H8, the Lewis, well, it's not the Lewis structure, it's showing more how it is broken down into a chain of carbons, and each carbon is surrounded by hydrogens. And so that means we only have carbon-carbon and carbon-hydrogen bonds. And we know these bonds are nonpolar, so it's a nonpolar molecule. So the list of intermolecular forces will always have the London dispersion forces. And here we have no dipoles, right? It's a nonpolar molecule. So there will be no dipole-dipole interactions. Another thing is the hydrogens are not bonded to oxygen, nitrogen, or fluorine. So there's no way you can have hydrogen bonding. So C3H8 only experiences London dispersion forces. C3H9N, we have a partial breakout of the structure here. It shows how we have the same chain of 3 carbons bonded to hydrogens, but there is one carbon that carries a nitrogen that is bonded to a nitrogen, and that nitrogen is bonded to 2 hydrogens to complete its octet. And that nitrogen has a lone pair, and if you remember the kind of structure it has, it's trigonal pyramid, right? So the nitrogen imagine the nitrogen up in the pyramid, and then one leg goes towards the carbon, and the other two legs are bonded to hydrogens. So, now if we look at the electronegativity difference between nitrogen and hydrogen, it's 3.0 minus 2.1. It's a difference of 0.9. So the NH bond is polar, and the NC bond is also polar because the difference is 0.5 between C and N. So we have a dipole. We have like three, bond dipoles going towards nitrogen, because nitrogen is the most electronegative element of the three. And so they add up because it's a trigonal pyramid. So they all add up and move upward towards the nitrogen. Oops. And so you can summarize the net dipole of the molecule as going up towards the nitrogen from the hydrogens and from the carbon. So we have a net dipole here, which means that this molecule will be experiencing dipole-dipole interactions in addition to the London dispersion forces. Now, do we have hydrogen bondings? For hydrogen bonding to be possible, you need hydrogen to be bonded to nitrogen, oxygen, or fluorine. And here we have hydrogen bonded to nitrogen. So this molecule can experience hydrogen bonding. So it experiences all three of the intermolecular forces. Now let's look at C3H7F. The Lewis, or the partial structure here, is given. So it's again the same chain of 3 carbons, but there is one carbon that is bonded to the fluorine. Fluorine is a peripheral atom. It cannot make more than one single bond. So that's why, it's just bonded to a carbon. Instead of having a hydrogen, the carbon has a F bonded to it. So is this a polar molecule? So we have CC bonds, CH bonds that are non-polar, but we also have now this CF bond. And the electronegativity of fluorine is 4.0 minus 2.5 from carbon. That's a large difference that makes this bond polar. So the CF bond is polar towards the fluorine. And there's nothing to cancel that polarity because all other bonds are non-polar. So the molecule will be polar towards the fluorine. So we can have dipole-dipole interactions between molecules of C3H7F because of these dipoles. Now, do we have hydrogen bonding? For hydrogen bonding, we need hydrogen to be bonded to oxygen, nitrogen, or fluorine. And here we have fluorine, but hydrogen is not bonded to fluorine. So hydrogen bonding is not possible, because the fluorine is bonded to carbon. So no hydrogen bonding for this molecule. So now the question was asking to rank them in order of intermolecular strengths. So to the left, we'll place the weakest of the molecule, and that should be C3H8 because it only experiences London dispersion forces. To the right, we will have the most, the one that experiences the most intermolecular attractive forces. And that can be H2O or C3H9N. And so the molecule that has the fluorine will be in between. And so we will have water being the strongest, experiencing the strongest forces, because water is a smaller molecule and it's easier to put together and orient the molecules such that the hydrogens face the oxygen, and you can have, a very neat arrangement of water molecules in the case of water. In the case of the molecule with the nitrogen, it's more difficult to arrange the molecules such that the nitrogen is facing hydrogens bonded to a nitrogen, right? Because be careful, the hydrogen bonding occurs between the hydrogens that are bonded to nitrogen and the nitrogen atom of another molecule. So because this molecule is more cumbersome, it's more difficult to have the, enough hydrogen bonding. So that will make it less strong for this molecule versus water.